Hello everyone, and welcome to this comprehensive tutorial where we'll not only implement a linear support vector classifier from scratch, but also dive deep into understanding the logic behind it. Before we get into coding, let's first take a moment to understand what we're building. An SVM, SVC, like a linear support vector classifier. It is a supervised machine learning model used primarily for classification tasks. It's based on the idea of finding the best separator or like a hyperplane that separates data points of different classes with maximum margin, preferably. This concept of margin is key, and we'll unpack it as we go. Now, it's important to remember that while machine learning libraries like scikit-learn have optimized versions of SVC, but there's immense value in understanding how it works behind the scenes. Building models from scratch not only gives you a deeper understanding of the mathematics involved, but also enables you to appreciate how these methods scale to real world problems. By the end of this video, not only will you have built your own linear SVC from the ground up, but you'll also be able to apply this knowledge in other machine learning tasks. Before diving into code, let's discuss the foundational concepts of SVMs. What exactly are we trying to achieve here? Well, think about this. If you have the dataset where two different types of flowers were presented, how would you classify them into their respective groups? You could simply draw a line that separates these groups. But here's where SVMs get clever. Instead of just any line, it tries to find the line that maximizes the distance between the closest points of each class to the decision boundary. This margin maximization, what it does, it helps SVMs generalize better to unseen data because what happens is the points are pushed as far as possible from the boundary. This idea of margin optimization, it is one of the key differences between SVMs and other linear classifiers like say logistic regression. Next, let's briefly talk about the linear aspect. A linear SVC, what it means is that we are assuming our data is linearly separable. What it means is that there exists a straight line or a plane that can separate the data points of different classes. If your data isn't linearly separable, you typically move to more complex methods like kernel SVMs. But that's a story for another day. But for now, we are focusing on the linear case to simplify things and focus on the core idea. Okay, now that we understand what we're building, let's start with the code. I'm going to walk you through a linear SVC class where we encapsulate all the logic for training and predicting. First up, let's talk about the initialization. This is where we define our parameters. In a support vector classifier, some key parameters control how the model behaves. Let's break them down. Okay, so the first, this is the C parameter. What it actually means is it is the regularization parameter. It controls the trade-off between having a large margin and correctly classifying the training data. A smaller C, what it will do is it will create a softer margin. What I mean by softer margins here is that some misclassifications are allowed, while a larger C, that would mean just stricter margin with fewer misclassifications. In practical terms, what it does is helps with overfitting or underfitting the model, right? Okay, and learning rate. So learning rate and iterations, what they do is these parameters control how quickly or slowly our model learns. The max iteration parameter, which we have defined, what it does is sets the maximum number of iterations the model will go through during training. the learning rate initialization. Here, okay, so the learning rate initialization, it is like the initial state at which our model updates the weights. If this is too high, we may overshoot optimal solutions, and if it's too low, training could take forever, which we don't want. Okay, next up, what we need to know about is tolerance. So, tolerance, it controls when we stop training. Essentially, it says if the improvement in the loss function is less than a certain threshold, we can stop early, right? Okay, and now finally, early stopping. What it does is monitors the model's performance on a validation set. If the performance stops improving after several iterations, we halt the training to prevent overfitting. That's like a safety valve to avoid overtraining our model on data. Okay, next let's discuss the heart of the training process, which is the gradient descent, right? Every machine learning algorithm that's using gradient descent, what it does have is a learning curve. In our case, what we're doing is we're minimizing the cost function, which helps us to adjust the weights to make better predictions, right? But why do we need to adapt the learning rate? Imagine you're trying to climb a mountain in the dark. If you take big steps, you might overshoot the peak, right? But if you take smaller steps, you risk taking too long to reach the summit. This is where adaptive learning rate comes in, right? Which we have defined here. Here, what it does, it helps us adjust the step size dynamically during training to find the right balance between speed and accuracy. Okay, so we implement adaptive learning in our adaptive learning rate function. It adjusts the learning rate at every iteration based on the current step. So we gradually take smaller steps as we near the optimal solution, right? Okay, so what we do now is go for the training part. Here, okay, so let's move on to the fit method. This is where the actual training happens, right? This is where we tie everything together. So yeah, we initialize our weights to zeros, and then for each iteration, we make predictions based on the current weights and bias. We calculate errors, compute the error between our prediction and the actual labels. Using gradient descent, we update the weights and bias by minimizing the cost function. And what we also do is track the cost function. Using the cost function, it helps us to measuring how well our model is performing. By calculating the cost at each step, we can monitor the progress of the learning algorithm, right? Okay, one important note, the gradient, wait, there's this special, yeah, okay, this is where it is. So this gradient underscore W and gradient underscore B function, what these are, These calculations, these are like essential for updating the weights and bias. These gradients, they measure how much the error changes when we change the weights even slightly. This is why gradient descent is so powerful. It helps the model learn which direction to update the weights to minimize the error. Isn't that amazing? Okay, now moving on to the predict part. Okay, so the predict method, it is quite simple but very important. After training the model, we use it to make predictions, of course. These predictions are based on the weight sum of input features plus a bias term. If this sum is greater than 0, we predict class 1. Otherwise, we predict class 0. That's how it works. We also have an option to return probabilities. For example, by applying a sigmoid function to the linear output, we get a value between 0 and 1, which represents the probability that the input belongs to class 1. This part may seem trivial, but it's what allows our model to actually be useful in real world applications. Okay, so yeah, before we train our model, we need to prepare the data, right? Preparing of the data for our model, that's important. Okay, and preparing of the data, what we have done is uh, scaling, some little scaling, and then we have split the data into training and testing sets, of course. Okay, it's essential to have a test set to evaluate how well our model generalizes to unseen data, while for standardization, it's one of the crucial steps. Okay, it ensures that all features are on the same scale, which is important for algorithms like SVC because they rely on gradients. If one feature has a much larger scale than others, it can dominate the learning process, leading to poor performance. We use standard scalar here to standardize the data, right? Okay, so this is hyperparameter tuning. What we're doing here is we're trying to find the best model. It is one of the most crucial steps. Okay, while our model can learn the weights and bias during training, there are certain parameters like the regularization term C and the learning rate that we have to set manually. These hyperparameters can drastically impact the performance of our model. So in this section, what we do is we perform a grid search, right? What we do is we perform a grid search to find the best combination of hyperparameters. We test multiple combinations, as you can see, train the model on each combination and select the one that performs the best on our validation data. This is an important step in machine learning workflows as choosing the right hyperparameters can make a significant difference in model performance. Okay, now moving on to the part of evaluation. Once we have trained the model with the best hyperparameters, it's time to evaluate its performance. We calculate the accuracy on the test set, but accuracy alone doesn't always give the full picture. That's why we also look at this confusion matrix right here, which tells us how many of our predictions were correct or incorrect in terms of true positives, true negatives, false positives, and false negatives. The decision boundary is it's another useful way to visualize how well the model is separating the class, right? By plotting this boundary, what we're doing is we can visually see how the SVC is working. Does the decision line make sense here? What do you think? Given the distribution of the data, is the margin large enough? Okay, I will let you take in the code yourself one more time. So, yeah, by now you have much deeper understanding of how a linear SVM works and how to implement it from scratch. We covered everything from the theory behind SVMs, understanding hyperplanes, margins, and the cost function, to the implementation details like gradient descent, adaptive learning rates, and how to adjust the weights and bias. Okay, we walked through the steps of preparing the data, building the linear SVC class, training the model, and finally making predictions. Along the way, we discussed key concepts such as the regularization parameter, learning rate tuning, and hyperparameter optimization, all of which play a critical role in improving the performance of our model. So, by implementing this, specifically this from scratch, what it does for you, we not only get a solid foundation to not only appreciate how libraries like scikit-learn work behind the scenes, but we can also customize and adapt machine learning algorithms for specific use cases. This is an invaluable skill as it allows you to innovate and modify models based on your own project needs rather than relying solely on prepackaged solutions. So that's all. As a final note, always remember that machine learning isn't just about building models. It's also about understanding your data and continuously refining your approach based on feedback from the results. Um, Thank you for joining me in this tutorial. If you found this helpful, feel free to explore more machine learning topics and experiment with different algorithms on your own. I am Shraq Ahmed. Happy coding.